common pair of kitchen scissors and a flour tortilla, cutting the pieces into some corn chips and rearranging those things, we were able to show that the area formula for a circle was based off of a parallelogram, a rather bumpy parallelogram. Let's look at the math, the algebra involved in actually coming up with a formula that area is equal to pi r squared. All right, so I've duplicated the picture here, and we need two pieces of information if we are going to derive the formula, because the area of a parallelogram of course is base times height. So we need a base length and we need a height. So our base is this bumpy segment down here, and it's the same length as this bumpy part right there. If you string all of that together, of course, that is the circumference of the circle. And I've got half up top and I've got half on the bottom. So the base length down here is 1/2 of the circumference. And now we need our height. And the height is rather easy. The height is just this segment length right here on all of these corn chips, which is the radius of the circle, right? It would be this length right here, or even one in between those corn chip edges. This is the radius. And so now I have enough information to piece together what the area formula for a circle is, and that is 1/2 of the base length, 1/2 times circumference, and then multiply it times the height, which is our radius over here, times r. And there you have it. Very elegant, right? That's exactly the area formula for a circle that we wrote down when we... No, it's not. It's not. There's some stuff missing. There's no pi in there, and, you know, believe it or not, I don't think that there is a 1/2 in the area formula for a circle. All right, so there's more to do here. There's a little bit more to do, and it has to do with the definition of pi. So the definition of pi is the ratio of the circumference of a circle to its diameter. So pi is defined to be circumference divided by diameter. And now what I'm going to do is I'm just going to rearrange some of the pieces here. It's a literal equation, basically. I'm going to take my circumference formula. I'm going to multiply both sides by d. I need to solve this thing for c, so I can substitute that c inside there, all right? So I'm going to multiply both sides by d, multiply by d. And that will cancel out the d's on the left-hand side, and I'm left with d times pi is equal to c, right? That was one of the circumference formulas that we talked about. So now I can take this and substitute it in for c right there. That's exactly what I'm going to do next. I'm going to take that and substitute it in for c. So now my formula becomes 1/2 of d pi times r. There we go. There's the area formula as we... No, again, it's not. It's still wrong. One other thing. We have another, I guess, relationship that is supposed to be true for a circle, and that is that a diameter is equal to 2 times a radius. So this is really a system of equations that we've got going on here. We're going to have to do lots and lots of little substitution. I'm going to now take my d equaling 2r, and I'm going to substitute it in for this d that's right there. Now my area formula is equal to 1/2. Instead of d, I will write 2r, then we have our pi, and then we have our other r. It's on the outside of it. Now we're getting closer. So we can kind of use the associative property and the commutative property to rearrange a few of these things. Like, for example, I can take this 1/2 and I can multiply it by 2 and I get 1 and it disappears. And then I have my r multiplied times this r to make an r squared. And finally, we see the area formula as pi times my radius squared. All right, so if I come back to my picture, I know you're kind of scratching your heads. When we did it in the kitchen, we divided our corn tortilla up into exactly 16 pieces. But what if we made more pieces? Let's take a look at a Desmos sketch of this, where I can actually change the number of pieces. So right now you can see that I have my circle, my original blue circle that is up top. And then down at the bottom where it says radius r, I've basically cut it into one piece, which means I've cut it not at all. And I have a slider up here at the top. It says n equals 1 right now. That means one slice. And then I can move that slider so that I have, say, 2, 3, 4, 5 slices or something like that, right? So we did it so that it originally had 8 slices, and then we were able to make, say, 16 slices. I can actually hit play on this one and see what the heck is going to happen. So now take a look at that shape. As I increase the number of sides, not only does it start to look like a parallelogram, it's actually starting to look like a rectangle, right? More and more and more slices. This idea of being able to take those slices and make them as small as possible, this is related to something that we do in calculus called limit. And there you go, at 200 slices, I'm going to hit stop here and then hit pause, pause it. There we go, and go all the way up to the 200. You can see it's almost indistinguishable from a rectangle. And there we have it. There's all of the area formula that we talked about related back to a square as an axiomatic system, right? And so there's the area formula, pi r squared.